So this first story from space.com, James Webb Space Telescope snaps stunning view of supernova's expanding remains. I've talked about supernovas before. It is when a star that is big booty, as I like to call them, a big booty star, when they get many, many times the mass of our own sun, they reach the end of their lives, they explode. As a result of those explosions, many new elements are created, many new different in terms of the periodic table, many those types of elements are what I'm talking about. Those are created, but it also creates, as you can kind of see in this photo right here. This is supernova 1987A. You can clearly see that in the middle, it looks like an eyeball almost, but if you kind of think about it, this was once a star and it has exploded in those outer regions. You can see a remnant of the outermost part of the star. And then as you look inwards, that different color right there, I'm this is the near cam. So this is near infrared. So this is almost infrared. So this is not truly what it actually looks like in real life. Let's keep that in mind. This is mostly about temperature, I believe, for infrared. But you'll see in the center, you'll see the makings of a different set of properties and most likely elements as well. So this is the one that was snapped earlier. But let's get into the story. The remains of a star that exploded 36 years ago have fallen under the gaze of the James Webb Space Telescope. And this observatory's near-infrared camera captured the expanding stellar debris in unprecedented resolution, revealing brand new details about this burgeoning supernova remnant. This is the closest observed supernova since Kepler's supernova lit up in the Milky Way in 1604. A lot has changed since then. This star explosion was first identified in 1987 and is aptly known as supernova 1987A. It sits about 168 light years away from Earth in the large Magellanic cloud and represents the destruction of a bright blue supergiant star called Sundaleic 69202. Before it exploded, that star was thought to hold a mass about 20 times that of the sun. So it's a big star, but it's not massive. It's a good sized star. Hence why it exploded in a massive supernova, because it is so large. So bright was this supernova, in fact, that it was visible to the naked eye in the southern hemisphere, and astronomers have been tracking its expanding debris ever since. Now the JWST has been brought to bear on the supernova's remnant in a study led by Mikakaku Matsuru of Cardiff University in the UK. All right, so this guy used the JWST to measure the expanding supernova shock wave as that wave interacts with surrounding material. When a massive star such as blue supergiants, which is what this is, near the end of their lives, they become unstable and beginning throwing off large amounts of matter. And blue supergiants, so to kind of break that down, blue as in the temperature of the star, and a high temperature when we're talking about a star changes the actual color of the star, because it's going through nuclear fusion a lot hotter, and that hotness comes off to our eyeballs and our telescopes as blue. And then supergiant obviously it's not just a giant star, it's a supergiant. So 20 times the mass of our sun. Pretty good sized star. The Hubble Space Telescope had previously watched as supernova 1987A's expanding shock wave, initially traveling at about 4,350 miles per second, caught up and collided with a ring of circumstellar debris ejected by the Doom Star during the 20,000 years or so before it went supernova. As the wave clashed with this ring, it slowed to about 1,430 miles per second. In the grand scheme of the cosmos, that is not that fast. However, it still is fast. I mean, let's be honest. Relative to driving a 2006 Toyota Corolla, it's definitely fast. Clumps within this ring gradually brightened, appearing as a bracelet of pearls. Two other rings, which appear to be in a different plane to the main rings as well, as thinner and more faint, are more mysterious. Astronomers have speculated these rings could be where the star's stellar wind, emitted before the supernova, interacts with material the star previously ejected. And you can see right here, they kind of talk about the actual light itself. You can kind of see a little cool little, I want to say that that's gravitational lensing, but I could be wrong. In the background right there, the JWST will continue to monitor the expanding supernova remnant as it evolves, as well as the search for the neutron star at the center of the explosion. There is, however, indirect evidence for the neutron star in the form of X-ray emission detected by NASA's Chandra and NuStar X-ray observatories, as well as observations by the Atacama Large Millimeter Submillimeter Array. Indicates the neutron star could be hitting within one of the clumps of dust at the heart of the remnant. And then let's just click on neutron star right here, so you can kind of see. Neutron stars are the remnants of the cores of massive stars that have reached the end of their lives. They are one of the two possible evolutionary endpoints of the most massive stars, the other being black holes. The densest stellar objects, apart from perhaps whatever exists at the heart of a black hole, neutron stars are some of the universe's most extreme objects. Even stars with masses between 10 and 20 times that of the sun reach a limit to the heavy elements that they can forge, usually ending up with a core of almost pure iron. Even this heavy element isn't dense enough to prevent massive cores from further collapse. As this occurs, the gravitational pressure is so intense that the negatively charged electrons and positively charged protons that comprise the iron nuclei in the stellar core are crushed together, creating a sea of uncharged or neutral neutrons. Some massive stellar cores are at this point saved from further collapse by a quantum phenomenon called neutron degeneracy pressure, which occurs when such a density is reached that neutrons can no longer be packed any closer together, leaving them as neutron stars. The key difference, now this is referring to this in black holes, seems to be the collapsing stellar core possessing enough mass to exceed the protection that neutron degeneracy offers neutron stars. Currently, the scientists aren't exactly sure where the delineation line between black holes and neutron stars lies. This uncertainty exists because the physics inside neutron stars remains difficult to investigate. Okay. So, yeah. And then it kind of talks about our own sun. When the sun reaches the end of its hydrogen supply in about 5 billion years, and the outward pressure protecting against gravitational collapse ceases, its core will collapse. After passing through a red giant phase during which the sun's outer layers will swell out and swallow the inner planets, including Earth, the sun's core is left as a smoldering white dwarf. So it's not massive enough to have that much amount of pressure, and also to create those elements that we need for life as we know it here on Earth, such as carbon. Neutron star. This is a crazy image right here to kind of show you the size. So this is, if you can see in the picture, New York City, downtown New York City, downtown Manhattan, New York, New York. I want to be a part of it. And that thing over there to the right, that blue guy, is a neutron star with the mass of our own sun. Now, our sun is a little bit bigger than our own planet, correct? So just now imagine one of those that is maybe 10 or 20 times the mass of our own sun. It's still not, in terms of size, it's not super big, but it's just packed so densely and so tightly that it takes up a little amount of space. Very cool. So this is one of the things that JWST has captured. Let me accept all the cookies. How about we do that? This was an image that I saw earlier, the M51 Whirlpool Galaxy. Galaxy is about 27 million light years away from Earth in the Canes Venatici constellation and can sometimes be seen in our planet's night sky. It gets its Whirlpool Galaxy monitored thanks to the deep red and orange-like spirals around the edge of its bright white core, resembling water circling a drain. In the new image from the European Space Agency, the darker red parts show the galaxy's warm, dustier regions where complex molecules are forming on tiny particles of dust, giving off light. The orange and yellow bits are where gas has been turned into ions or charged particles by newly formed stars. Oh, and also the image is a combination of two separate pictures, one captured by the main near-infrared camera and the other by its mid-infrared instrument, will provide different perspectives on their subject by decoding infrared light signals. Yeah. Where's the image? What happened to the image? Well, this is the image right here. I guess this is the one we'll have to use, but you can see the detail from the James Webb Space Telescope, and hopefully we're looking at a galaxy that has intelligent life in it. I can only hope. And somewhere in this image there's an intelligent civilization, hopefully friendly. More about the James Webb Space Telescope. This is a cool article that I seen. If the Earth was an exoplanet, JWST would know there's an intelligent civilization here. So one of the main reasons why I am so fascinated by the James Webb is because of the literal nature of the James Webb, which is to look at exoplanets and try and see if there's life there. Try and look for other signs of life, intelligent or not, any kind of life out there in our own universe. Now, folks would say, well, if you're looking at something that's, say, 500 light years away, I mean, how could you even tell that there was anything on it? And that's a good question. And that's part of the reason why many people do believe that although we've not searched very much, that our searches have yielded no results, which leads people to say life is incredibly, especially life like there is here on Earth. Life is extremely difficult to start the process of. And we got very lucky here on Earth from literally millions of different factors. Some major ones are having Jupiter here, having those outer icy planets to help protect us from the Oort cloud or the giant meteors and asteroids that will come from the Oort cloud to Earth. And it also helps for us to have a moon as well. And it also helps that there was the many great different extinction events. And there was also the most famous one with the dinosaurs, but there's another one that I've talked about on the show in which about 90 to 95% of all life on Earth was completely wiped out. And that was a big reset. The Permian extinction is the name of that. All right, so this article here. If we're going to look on other worlds, why not start with the one planet we know has life? Earth's atmosphere is rich with oxygen and molecules such as methane, which strongly suggest the presence of life. It also has traces of molecules such as nitrogen dioxide, and CFC, commonly known as Freon, which are strong indicators of an industrial civilization. As a recent study shows, if Earth were an exoplanet, JWST could identify these molecules in our atmosphere. Now, I think that's an interesting classification for this is what an industrial civilization would be doing. This is what the presence of life is, right? If you see these elements, that is evidence that there is life. And the basis for that is because that's how it happened here on Earth. That does not mean that inherently on these other planets that there is life that abides by these rules of nature that we have here on our planet simply because they are not Earth. There's not going to be a 100% direct copy. Our atmosphere is finely tuned and finely intertwined with the life forms that live upon it. So is there an argument that on a different planet, there still is water, there's still some of these things that we are accustomed to on our planet, but the atmosphere is a little bit different. There's maybe the dominant type of element that makes up the air is not oxygen. Maybe it's a civilization that can survive off of carbon dioxide because they evolved in a certain way from us. Now, we do not know because we have not, one, found life elsewhere, but two, we also can only judge life in our universe based on one example. So there are pros and cons when you are looking at different exoplanets and seeing, oh, this one has an atmosphere. What's that atmosphere made up of? These lists of elements that we have here on Earth. I mean, it's the best formula that we have right now for finding these other civilizations, but I don't think it's foolproof for obvious reasons. That's not earth-shattering, but I just wanted to point that out. The study starts with real observations of Earth's atmosphere. The Canadian satellite SciSat took high-resolution spectra of sunlight passing through a cloudless region of Earth's atmosphere, and from this identified a range of natural and synthetic molecules using an averaging of the data across current atmospheric depths. And earlier studies simulated the possible spectra as it would appear when Earth transits the sun seen from the outer solar system. This provides a good baseline for what exoplanet data could be obtained. And you can see these are the different wavelengths of life, and you can see I'm just assuming that the left axis, effective transit altitude, I would imagine that is just the concentration of it that's in our atmosphere. I could be completely wrong. And then on the bottom is obviously wavelength of light. Different elements will have different wavelengths of light when you shine a light through them, and this time it being our sun. The authors then took this to the next level by roughing up the data, adding simulated noise to the signal, and then sampling at lower resolutions. This is similar to the kinds of observations JWST would make on an exoplanet light years away. The goal was to determine if enough data could still be captured to identify atmospheric models, even when the observations are faint and noisy. Sure enough, the signal to noise ratio was strong enough to identify many of the molecules for an Earth-like planet within 50 light years of Earth. Huh. Yikes. So in the grand scheme of things, that's not very far away. Not billions and billions of options for civilization within 50 light years from Earth, unfortunately. The team then took the idea a step further and considered the exoplanet system known as TRAPPIST-1. It's a system 40 light years away with 7 known planets 2 or 3 of which are potentially habitable. By introducing molecular spectra into the simulated spectra of TRAPPIST worlds, the team showed that JWST could identify both biological signatures and technological signatures should they exist on a TRAPPIST exoplanet. They still want to be able to identify alien structures on this world, but we don't need to go that far to prove the existence of aliens. JWST can identify oxygen, organic molecules, and synthetic molecules such as CFCs in the atmosphere of a nearby exoplanet. Then we know an intelligent civilization either is or was present here. So I do suggest that you take a look at the all the things that the web is doing. This is back to our supernova that we saw earlier. Just crazy. The possibility of finding a different exoplanet within 50 years is a difficult task. Not impossible. Not impossible. We just got to keep looking. Right? Well, the possibility of finding an intelligent civilization within 50 years, I've talked about it before, the Drake equation. You apply whatever variables you want to plug in for it, and apply that to an area of 50 light years around the Earth, and your chances of finding an intelligent civilization somewhere close with Earth is not very high. Not very high. And also, one of the issues of this particular study, not that I don't think it was valid or anything, but the industrialization chemicals. Yeah. Currently, Earth in its current state has gone through many different industrial periods, but if you think of 1,000 years, 1,500, 2,000, 3,000 years ago, there was no industrialization. They were burning fires, yeah. They didn't have bulldozers and tractor trailers, 18-wheelers, factories. They didn't have any of that stuff back then. And it's very probable that other civilizations evolved hundreds, thousands, tens of thousands of years before or after us. So who's to say if a different civilization is even doing any of that industrialization just because they're much younger than us? Or they could be ones that are much older than us, but they evolved in a different way where they didn't do any industrialization like we do here on Earth for reasons that we do not know. All right, moving on. This is a cool video. I just want to show the video here. This is kind of a little simulation of a flight to Maisie's galaxy. This 3D visualization portrays about 5,000 galaxies within a small portion of the Sears Cosmic Evolution Early Release Science Survey, which gathered data from a region known as the Extended Groth Strip. As the camera flies away from our viewpoint, each second amounts to traveling 200 million light years into the data set and seeing 200 million years further into the past. The appearances, the galaxies change, reflecting the fact that more distant objects are seen at earlier times in the universe when galaxies were less developed. The video ends at Maisie's galaxy, which formed only 390 million years after the Big Bang, or about 13.4 billion years ago. Let's check this out. We're flying fast in this thing. 200 million light years in 1 second. Keep that in mind. Even still, you can see we're not moving very fast, but we are already about 30 seconds in. So that's a couple billion light years right there, making a nice left turn right here, you can definitely see a lot of these galaxies are getting darker and darker and darker. And now just imagine within each of these galaxies is billions and billions and billions upon billions of stars and potentially life. Just exciting to think of. All right, now we're going really far out. Got to travel a little bit of distance to see this. Wow. Damn. Very, very cool.